back to the class of differential equations and the matrices. We just talked about the linear independence of functions because we do consider functions as vectors too. So pretty much it's really the same thing, the same equation, vector equation, but each vector this time it is a function. Each vector here this time it is a function. And also, as I'm saying, a vector equation, you usually consider vector equation it is for a system. So we can take some specific value of t to generate the system. And even for those specific values, we know the system, the vector equation only has a unique solution. That means for all values of t, in order to this vector equation to be true for all values of t, the system, it is only allowed to take the trivial solution. So indeed, those three functions are linearly independent. But anyway, I want you to know to check the linear independence of functions. Indeed, there are different ways. I call this what I did in this example 10. It is by definition. And also somewhat practically more useful. To consider the linear independence function, you want to consider the Wronskian. Okay. So let's say we are having a set of two functions, and then the Wronskian of function of two functions. It is a determinant of 2 by 2 square matrix. First row is f1, f2, and then second row it's the corresponding derivatives. And similarly, when you have function of three functions, then the Wronskian would be a 3 by 3 square matrix, original functions, derivative of those original functions, then the second order derivative of those original functions. Okay, second order derivative of those three functions. And then, well, I hope you see the idea. If in general, the Wronskian of n functions would be n by n square matrix. They are generated in a similar fashion, like for two functions, three functions. Okay, two functions and three functions. And how about let's take a look one example, maybe two examples quickly. One example is we know cosine x and sine x, they're different. And now we want to show not only they are different, but more precisely, they are linearly independent. So for cosine x and sine x, what I did here is I calculated the Wronskian. Derivative cosine, that's negative sine. Derivative sine, that's cosine. And then for the determinant, you use the cross product, right? Forward the diagonal line, that's cosine squared, minus from the backward diagonal line. But anyway, keep in mind, there is minus from the diagonal line here. So minus minus tends to be plus. But I hope you know this very well, right? This is the Pythagorean identity, and it is just true for any angle x. Cosine squared plus sine squared equals 1. And indeed, we can say the set of cosine x and sine x, indeed, it is linearly independent. It is linearly independent. Okay. How about let's look at another example. I'm having three functions, and indeed, you can do the old-fashioned way like I did in example 10. Okay. And also this time, I'm using the Wronskian method. So for those three functions, I calculated the Wronskian. It is the determinant of a 3 by 3 square matrix. For the first row, you copy down those three functions. Then starting from the second row, you calculate the derivative. Then the second order derivative. And then for the determinant part, remember the determinant of a 3 by 3 square matrix, it can be expanded using any row or any column. At least I say you want to start from row or column with most zeros. So in this case, my calculation, what I did here is I expanded this determinant. I calculated this determinant using the third row because there's a 0 in the third row and the third column. So using the cofactor method, and this is 2, stay there. This 2 comes from row 3 and column 1. Remember, it always have negative 1 to the power. Row 3, column 1. And then minor, it is by crossing out where the row and the column is. That's the minor here. For the first number 2. The second number 2 comes from row 3, column 2. And the minor, it is from this here, right? And that there. And then, as I say, you want to do all the calculation because the remaining part, that is for the determinant of 2 by 2, I suppose that's rather easy. But anyway, still in this case, it does take a little time. And for me, I just took the number directly from the textbook. The determinant, that's a -8, which is not a 0. So according to the general conclusion of the Wronskian, this set is linearly independent. Those 3 functions are linearly independent. Okay, we are still in section 3.6, I'm sorry. We are in section 3.6. Section 3.6, it is really about the basis and the dimension. So now we get to the point about the basis and the dimension. And we say, given a vector space, it has a basis. If the set of vectors is linearly independent, and indeed, the span of all those vectors turns out to be the vector space entirely. So if that is the case, we call this set is a basis. And also the other quick thing to explain, the dimension. The dimension, it is the number of vectors in the set. The number of vectors in the set of bases. So in this case, if we say this is a basis, then the dimension, that's n. And maybe let's take a quick look if this would help. I think I did this one previously, but anyway, I'm trying to re-explain this again. Previously, I think we asked somewhat different questions, the span and the linear independence. So pretty much we are going to redo them again, and then we want to check if this set is a basis. First of all, according to the definition, we want to make sure if the set is a basis, and then it has to be linearly independent. So what I did here is I arranged those factors in a matrix fashion, and then determinant, clearly it is not 0. And for now, I want to say when the determinant is not 0, you could just say the set, the vectors from the columns. Okay, the column vectors are linearly independent. And also, I hope you can tell a little more why the determinant is linearly not 0. When the determinant is not 0, then the column vectors are linearly independent. Okay. And this is the first part requirement for basis. And also the second part requirement of the span. So I did check the second part of the requirement. And also, really, it is from the same situation. The determinant of the coefficient matrix is not 0. And then what I'm trying to show here is that any vector in the 3-dimensional space can be represented by those 3 vectors. And because the determinant, the coefficient of determinant here, it is not 0, which means it is not invertible. So the system always can be solved in this way. Which means for any vector A, B, C, it always can be written as the linear combination of those 3. So indeed, I'm saying this entire set, it is a basis. And also, if we go a little further, what is the dimension of the span? It is 3. The dimension of the vector space of R3 must be 3. Hey, thank you for watching. I'll see you next time.